Please confirm that you can see the presentation.
Yes, sir.
Okay, thank you. So let us resume our discussion from where we broke off in the last class, which was a week ago. So we talked about the various scales of the universe in the three mechanical dimensions of our common experience. I hope, incidentally, I'm sorry to interrupt once again. Please confirm that you can hear me clearly. Once again, I ask you.
Yes, sir.
Yes, sir.
Thank you. Thank you very much. Please mute your mic now. Thank you. So we acquainted ourselves with the scales of order of the three mechanical dimensions, namely mass, length, and time. And then we informed ourselves of the fact that the real dimensions of the universe, first of all, the scales of the universe, the actual scales of the universe are far greater than what we can experience through our senses. This small table says so. Then we informed ourselves of the fact that the real dimensions of the universe are set in terms of the fundamental constants c, h, and g, namely the speed of light, Planck's constant, and Newton's constant of universal gravitation. So let us see now what happens. So the first of the three constants we took up, which was the speed of light in vacuum, c, and we were looking through the implications of these fundamental constants. So one implication is that the speed of light in vacuum is invariant through all inertial frames or reference frames. Reference frames which are inertial in the sense that, I mean, any reference frame for that matter. I mean, it's actually a general principle. Now, the speed of light in vacuum is a universal constant, regardless of the relative velocity of frames that you travel in, which means that even if you travel at the speed of light, with respect to you, the speed of light will never be zero, will not be zero, but it will continue to be c. And so that requires a radical revision of the understanding of Newtonian mechanics. As per Newtonian mechanics, if you were traveling at a speed, with a speed u prime, in a certain frame of reference, which itself travels with the speed v or velocity v, speed v, then another observer who is on the ground will see your speed to be v plus u prime. So, but that doesn't happen when you bring in light into the discussion. So light will continue to have its speed regardless of how fast you are traveling with respect to it. If you're traveling at the speed of light itself, light will not show the speed to be zero, right? Which means, simple thing, light can never rest. When do you say that you are resting? When or something is resting. Something is resting when it doesn't move, which is to say its velocity is zero with respect to you. So you are traveling in a train. So one observer standing on the rail platform will see you have the speed of the train itself. You are traveling with that speed. But another observer who is traveling in another train parallel to yours in the same direction, that is, and having the same speed, will see you to have this velocity zero. So from the point of view of the traveling observer, you are at rest. So that is a matter of common sense. But then, as I said, the universe is operating on a very vast scale where things that we here, I've written this thing, the physical laws, example, Newton's laws, by which we understand the universe in the middle scales, need not be applicable either on very small or on very large scales. So this little formula U is equal to V plus U prime follows from Newton's law. But then this formula, which was set by Einstein, requires some serious revision of Newtonian mechanics. So as you can see, there is a lot to be known about the universe beyond what we can understand of it through the exercise of our senses or our common experience. So we have looked at one important implication of the speed of light in vacuum, that it is a fundamental constant. It's not going to change anywhere, regardless of the speed of your reference frame or regardless of your relative velocity. Meaning the speed of light is an absolute constant. It's an absolute velocity in the sense that there is no relative business about it. With respect to an observer on a rail platform, you have a velocity of, let's say, 50 kilometers an hour traveling in a train. But with respect to another observer who is traveling in a train with the same speed, parallel to your train, you are at rest. So different frames of reference will see different relative velocities. But light has no business of relativeness. Light has got an absolute speed. Okay, the second point. Our famous mechanical dimensions of mass, length, and time are not so sacred after all. Why not? Let us see. I told you that we experience the universe, mechanical universe, through three things: mass, length, and time. And these have been drilled into us through the natural process of evolution. But these three dimensions, the mechanical dimensions, are nothing very sacred. Let us see. This is again consequence of what Einstein stated. Mass, length, or did actually, a corollary of his theory of relativity. Mass, length, and time are not really invariant in various reference frames. Just like your velocity is not an invariant quantity. You are traveling in a certain, you are in a certain velocity state. Right at the moment, you may be at rest, sitting in your chair comfortably at home, but somebody who's driving past your house on the road will see from the driver, from his reference frame, will see you travel with us in the opposite direction, see you move in the opposite direction. So these are not, velocity is not an invariant quantity. Normal velocities, not the velocity of light or the speed of light. They are not invariant quantities. And so it is, mass, length, and time are not invariant either. Let us see how. Although we would think that they were very special. Let us see now. If m naught is the mass measured in a frame where an object is at rest, okay, and L naught is the length in a frame where an object is at rest, then in another reference frame moving with a relative velocity v, m and L are given by these two formula. M is equal to m naught by square root of 1 minus v by c whole squared, and L is equal to L naught into square root of 1 minus v by c whole squared. Let us try to have a little discussion on this thing. You have kept an object in front of you, let's say a book or something, a suitcase or whatever. It has got a certain mass which you can measure with a measuring scale, and you're leaving it on your desk or on your whatever, some piece of furniture, and you are sitting with it. So the mass that you have measured, this object is not moving with respect to you, right? The mass that you have measured is, let's say, 50 kgs. Fine. Now a driver is driving past your house in a car. So with respect to the car, the driver's frame of reference, your house, you and everything contained in your house, they're moving in the opposite direction with the speed of the car, except that the direction is opposite, right? The driver is driving at, let's say, 30 kilometers an hour, standard Indian bad road speeds. So you are traveling in the opposite direction. So the relative velocity that you have is 30 kilometers an hour. So 30 kilometers an hour divided by c squared will actually be a very small number, but it's still not non-zero, right? And so the driver will measure the mass of the object that you have measured to be m naught, let's say 50 kgs or something. The driver will actually measure it to have a larger value. From the point of view of the driver, the object will have a larger mass. Why is it larger? Let us now see. V is, notice one very important point over here from this formula. V can never be greater than c. We always keep saying that no speed can exceed the speed of light. This is why we say that. V can never be greater than c. Why not? If V were to be greater than c, then this ratio would be greater than 1. V by c would be greater than 1. And 1 squared will be a number still greater than 1. Let's say 2 is a number greater than 1. So 2 squared will be 4. Any number that is greater than 1 on squaring will give a larger number. than 1. So 1 minus a larger number than 1 will give you a negative number. Square root of a negative number is an imaginary quantity. Mass is still a measurable, real quantity. So mass can never be imaginary. Therefore, this is the reason why you say no speed may exceed the speed of light. So v will be less than c. So it will be a number less than 1. Squared, it will be a number that will be still less than 1. For instance, if I have a number that is less than 1, 0.9, let us say. 0.9 squared will give you 0.81. A square of a number smaller than 1 will be even smaller than the original number. And a square of a number larger than 1 will be larger than the original number. Make a careful note of that point, because this is something that we shall refer to again and again while we approximate things in our lab. In the last lab that we discussed, I hope you recall, I told you that we were going only up to the first order in the Euler formula, Euler numerical formula. Why not the second order? Why not the third order? You can very well ask me. The answer is that this usually the first order is a number that is smaller than 1. As a result, the second and the third orders will be even smaller, and we can safely neglect those numbers. We will discuss this thing later in more detail in the math class, whatever it is. So here we have this scenario. So this number in the denominator will be a number that will be 1 minus a number smaller than 1. So that will be a positive number smaller than 1. A positive number smaller than 1 square rooted will give you an even smaller number. So m naught divided by a number smaller than 1 will give you a larger value of m. That is the whole point. If you divide m naught by, let us say, 0.5, then actually the final answer will be 2 times m naught. 1 divided by 0.5 is 2, like that. So this is the way mass will be seen to have a larger value by an observer in relative motion with respect to your frame of reference. And the opposite happens for length. The length will contract. This is the famous formula of length contraction. Length will contract, meaning this ratio will be less than 1. So square root of a number less than 1 will be an even smaller number, and you're multiplying it with L naught. I'm not getting into the derivation of these formulae because that will require a proper and full understanding of Einstein's special theory of relativity. But I'm just giving you the end results whose implications I expect you to appreciate. So length will be seen to contract. Suppose your house has got a length of, let's say, I don't know, 10 meters or so, whatever. 10 meters or 20 meters, that's a big house. Maybe, yeah, 20 or 30 meters wide. And the driver is driving past your house. So from the point of view of the driver, if he's careful enough to make correct observations, then your house length, the width of your house will be seen to be slightly shortened. You'll see the implication of this thing that if you make v go to the speed of light, then you have a division by 0. So the mass will become infinitely large. And if you travel at the speed of light, then length will become 0. All of the universe that you see all around you, if you travel at the speed of light, the entire universe all around you will collapse to a point from your point of view. That is. Okay. So this length, L naught, is the length in a frame where the object is at rest. You have a ruler, a scale, a foot-long scale. You have it in front of you. You and the scale are at rest inside your room. So the length of the scale, 1 foot, 30 centimeters or so, is known as the proper length. You have measured the mass of a suitcase or some heavy object, and you have kept it in front of you. Both you and the suitcase are sitting tight, not moving around. So the mass that you measure of the suitcase is rest mass. With respect to you, the object is at rest. Therefore, the mass that you measure is known as the rest mass. But any other observer traveling with respect to you will see a different kind of a mass. Okay, so then you can very well ask me, why don't we see these things in real life? The answer is very simple. Look at the scale of it. Any velocity that you can produce through your feat of engineering, the speed of, let's say, a fighter plane, which travel at supersonic speeds, or even greater speeds of booster rockets, which lift satellites into outer space. What's the speed of that thing? Man-made technology. It's something like 11 kilometers an hour, 11 kilometers a second, 11 kilometers a second, right? Whereas light travels at 3 lakh kilometers a second, 11 by 3 lakh. That's the 11 kilometers a second is the fastest possible speed that you have achieved, right? So 11 by 3 lakhs will be an extremely small number. So how small? 11 by 3 lakhs will be something like 10 divided by 10 raised to 5. So that will be 1 by 10 raised to 4, right? That's the speed that you have. 1 by 10 raised to 4 squared will be 1 by 10 raised to 8. 1 by 10 raised to minus 8. So 1 minus of 10 raised to minus 8, you can neglect that. You will not feel any difference at all. 1 minus 10 raised to minus 8 will practically be equal to 1. So that is why even with the fastest possible speeds that you are capable of, the speed of booster rockets or satellites, it will be a negligibly small correction. You'll not be able to realize it. And not therefore to speak of the kind of speeds that you are capable of achieving in common experience, like a railway train, the fastest that they can travel will be about 100 kilometers an hour, something of that order. 100 kilometers an hour is nothing compared to the speed of light, right? Or even fighter planes, they travel at the speed of 300 meters per second, something of that order, because they travel close to the speed of sound, not light, close to the speed of sound. Occasionally, they exceed the speed of sound. And so if they exceed the speed of sound is something like 330 meters per second. So something like that order, 300 meters per second. Light travels at 3 into 10 raised to 8 meters per second. So you can see very well that these are things that we don't experience, but they do happen. When objects move at the speed of light, cosmic ray particles, for instance, then you will see these effects happening. Okay, what about time? So I told you, mass, length, and time are not invariant in various reference frames. You may think that they're very sacred, but they really are not. Different observers will say, I've got this number, you've got this number, and why can't we agree? Well, you can't agree because because these are relative quantities, nothing very absolute quantities. Okay, if the same thing happens with time, we have talked about mass and length, now we talk about time. T naught is the time measured, if T naught is the time measured between two events that have occurred at the same point in space. This is a particularly important thing, that have occurred at the same point in space. Then in another frame moving with a relative velocity v, T will have just exactly this formula. Whatever I have discussed for mass, the value of mass increases. Similarly, the value of time increases. This feature is known as time dilation. Let us have a little detailed discussion on this point. If T naught is the time measured between two events that have occurred at the same point in space, this line is particularly important, that have occurred at the same point in space. What do you mean by occurred at the same point in space? You are traveling in a train. You are sitting in the train and you're feeling a little bored. So you want to have a little entertainment. What is your entertainment? Follow this discussion carefully. You are taking a coin or a tennis ball or whatever, and you're tossing it up and down. So you are sitting at your position in space, in your railway seat, carriage seat, and sitting while you are throwing the object up. It is going up a certain height, then it is coming down, and you are catching that object. Right. So between these two events, what are the events? Your releasing of the tennis ball or tossing of the coin, and that is the first event. And the second event is your catching that tennis ball again as it has dropped back into your palms, in your hands. So these are the two events. Now, both these two events, as far as you are concerned, have happened at the same point in space, namely where you are seated. You are sitting in your seat, you've thrown the object upwards, it's gone up, then it's come down, you've caught it. So both these two events have occurred at the same point in space where you are seated. But a certain amount of time has elapsed between the two events. How do you mark time? By causing events. Like, let us say, your watch. Your watch is constantly creating events. What do you mean by constantly creating events? Like at this moment, it is somewhere around 12:20, meaning the hour hand is coinciding with the groove of 20. That is the first event. 5 minutes later, it will shift to the groove of 25. So between the two of them, you have these two events, 5 minutes would have elapsed. So you mark the passage of time with the help of marking events. So when you talk about events that have occurred at the same point in space, such as your little game of throwing a tennis ball up and catching it back again as it falls down into your hands. Uh, what you measure in between these two events is known as proper time T naught. T naught is the time measured between two events that have occurred at the same point in space. Okay, but you are traveling in a train and you are engaged in playing your little game of tossing the ball up and catching it as it falls down. Both are occurring at the same point in space, namely your seat. As far as you are concerned, you have marked proper time. What about an observer who's standing on the ground? Let's say that the train has got glass windows or broad glass windows. And the observer standing on the ground sees you going past. This observer will see you release the ball at a certain point in space, which he marks. And then by the time you capture the ball back, after it has fallen back, from the point of view of the ground observer, the ball capturing has happened at a different point in space. Incidentally, the ball will follow a parabolic trajectory. The vertical motion will be governed by the Earth's acceleration due to gravity, and the horizontal motion, as far as the ground observer is concerned, not you, the ground observer is concerned, will have the velocity of the train. The ball will also have the horizontal velocity of the train because it is a part of the train. And so the ground observer would would see the ball to follow a parabolic trajectory. Incidentally, in your later laboratories, you will have a lot of work to do involving projectile motion. Projectile motions, I believe, you have studied in your class 12 physics, follows a parabolic trajectory. Right. So the ground observer will see the same two events, which you see to occur at the same point in space. The ground observer will see those same two events to happen at different points in space. Therefore, from the point of view of the ground observer, the two events will take a longer time to happen. Why? The same formula as I said, when you divide m naught by a number smaller than 1, mass will increase. Same status time has. Time, T naught, proper time, the the observed time by an observer who is in relative motion with respect to the proper frame of reference where proper time has been measured will see a longer time. So you see a ball tossing experiment being done by throwing an object up and down. So you measure this event on a time scale of, let us say, 1 second. An observer on the ground will see the same two events to take a longer time. So that is the process of time dilation. Dilation means things will become enlarged. So as you can see, you have rest mass, you have proper length, and you have proper time. Rest mass is where the object is at rest and the mass has been measured accordingly. Proper length is where the object in a frame of reference where the object is at rest and the length has been measured accordingly. Proper time is the time that has happened between two events that have occurred at the same point in space. So all these three quantities, mass, length, and time, will vary as you go from one frame of reference to another. So they are nothing very absolute from the point of view of the universe that is operating on a much vaster scale. What is absolute is actually the speed of light. That is absolute. It is a fundamental constant. Okay. So we have seen the second implication of the absoluteness. This thing would not have happened if Einstein did not say that the speed of light we would not have realized if Einstein did not say that the speed of light is an absolute fundamental constant. Let us now look at the third implication. So the third implication is that the scalar length of an object actually doesn't vary. Let's see. Let's look at this simple diagram. I have given you a length of an object which is in the coordinate system, which is to be measured in the coordinate system xy. This full continuous axes x and y define a coordinate system. And with respect to this coordinate system, you have a stick or something, a long ruler whose origin is coinciding with this coordinate axis. And so this ruler is has got a certain length L. What is the length L of this ruler? It is L squared is equal to x squared plus y squared. Very good. Now what you do is that you keep this axis fixed. I mean this origin fixed, and you rotate the axis. So x axis through a rotation, like just the way you rotate the steering wheel of a car. You rotate this axis. The new axis is this dotted horizontal axis x prime, and likewise the y-axis has also rotated, because between the two of them, they will be still subtending an angle of 90 degrees. Okay, so there you are. But this rod you have not changed. Its length still remains the same, and its position is still the same from its own point of view. You have just only rotated these set of coordinate axes, and therefore, from the point of view of the new coordinate set system, the length of the rod will still be the same, and it will be given by this Pythagorean relationship. I hope you are aware of this fact. L squared will be equal to x squared plus y squared. By this Pythagorean relationship, x prime squared plus y prime squared. Okay, that is a very simple thing to understand. Now you extend the principle to 3 dimensions. I've just drawn a diagram showing 2 dimension. It's a 2-dimensional diagram on a page, on a sheet of paper. But you can easily extend the principle in your mind to 3 dimensions, and you can see that the same principle will hold. In 3 dimension, the scalar length of an object, L squared, will be equal to y squared plus x squared plus y squared plus z squared. And if you rotate the axes by keeping the origin fixed, you will get x prime squared plus y prime squared plus z prime squared. So it will be the same in both coordinate systems. Now comes something very important. That much is, this is something that you learn at school, really. Now, this is Einstein's doing. When objects move close to the speed of light, the invariant scalar length that is measured is not this, x squared plus y squared is equal to x prime squared plus y prime squared, or this in 3 dimension. The invariant scalar length becomes invariant in a 4-dimensional coordinate grid, x squared plus y squared plus z squared, like before, x squared, x prime squared plus y prime squared plus z prime squared. If you were to just take these 3 things, then the scalar length L squared will not be invariant when you travel close to the speed of light. What will make it invariant is the addition of these 2 new things, minus c squared t squared minus c squared t prime squared. So basically, when you live in the universe that you actually live in is a 4-dimensional universe. It's just that you do not realize this. It's a 4-dimensional universe. Why do you not realize this? Because the speed of light is such an enormous quantity, and then there is something else to it. Let us look at this thing. X squared, y squared, z squared, all with a plus sign, but here you have a minus c squared t squared. Basically, when you write x squared, y squared, z squared, you have coordinates x, y, z. But when you have minus c squared t squared, the coordinate is not ct, because you have to take the square root of this quantity. The coordinates are the square root of these squared quantities, right? So when you take the square root of minus c squared to t squared, it is your ICT. I as in the square root of -1, c and t. Basically, the universe that you actually inhabit is a 4-dimensional universe, X, Y, Z, and ICT. And now you can very well say, why can't we make sense of the 4th dimension? This short answer is that it's because of this I. You don't see, like you see an X coordinate, Y coordinate. You're sitting in your room right now. You just look at the corner of your room. There's a vertex. There's an X-axis going in one direction, perpendicular to it. Along the floor, there's a Y-axis on the floor. And then towards the ceiling, the 3rd axis rises. That is the Z-axis. So you should say that, can't we see the time axis like that? You can't, because of this I business over here. Time is not imaginary. But the axis, this is just like your Argand plane in complex numbers, a complex algebra. You have a real axis, x, and you have a so-called imaginary axis, but you call that imaginary axis I into y. Y is not an imaginary number, but the axis along which y is going is an imaginary axis. So the actual number that you have, you write it as x plus iy, something like that, or a plus ib. Here, x, y, z are real quantities, spatial coordinates, and time is traveling along an imaginary coordinate. But be careful once again to note that time is not imaginary. Just like when you write x plus iy, both x and y are real numbers, uh, but y is a so-called imaginary axis. So this is something like that. But the more important, I mean, let's not get into too much of the math business. What is happening over here is that time and space are now unified in this four-dimensional coordinate system. Time and space become, so basically when you see one after the other, your mass, length, and time are suffering serious setbacks. First of all, they don't have universal values through various reference frames. Fine, that's one trouble. But then the next thing, length and time. Length and time, we thought they were two separate physical categories. They were separate physical dimensions. But Einstein has now unified them in the same four-dimensional grid. You notice this thing: x, y, z are all length squared dimension. X squared was the length squared, but this thing c squared, t has the dimension of time, but c squared into t squared, c squared, c has the velocity per time. So velocity squared per time squared into time squared will again, sorry, length squared per time squared into time squared will again give you length squared. So this is dimensionally properly compatible, no problem there. But the thing is that the universe reality, in reality, the universe is actually a four-dimensional coordinate system, and time and space are now unified. We should not be seeing them as two separate categories, physical categories, and this unification is possible because of the invariance of C. You see this thing, this c squared and this c squared over here. The c is, I mean, I have written x, y, z, and t here. I have written x prime, y prime, z prime, and t prime here, but I have not written c prime here. Why not? Because c is going to be the same through all frames of reference. So this unification has been possible because of Einstein's showing that the speed of light is invariant through all frames of reference. So c is a universal constant, and it establishes, the last point is the famous formula of Einstein, E is equal to mc squared. So it establishes an equivalence between mass and energy. So earlier you would think that energy is a conserved quantity, mass is also a conserved quantity, energy is a conserved quantity, was shown by all the people who discovered the laws of thermodynamics, Joule, Lothar Meyer, all of them. Joule, after whom the energy unit is named in the SI system. And then Lavoisier, the father of modern chemistry, showed that mass is a conserved quantity. You take hydrogen and oxygen, put the two together, you get water, H2O. But nevertheless, the mass of hydrogen and oxygen taken separately, being separate, but the total mass of hydrogen and oxygen will equal the mass of water, right? That's as far as Lavoisier goes and all those things. But when you go to the nuclear domain, in nuclear chemistry, there is something called mass loss. What happens to that mass? You would have studied this thing in school, I think. Mass defect. Mass defect, I'm sorry, not mass loss, mass defect. There's a slight difference between, let's say, in a fission reaction. We will discuss these things in detail later when we take a physical system, mass defect. So you start with two particles, let's say uranium-235 plus a neutron, and then the neutron taps the uranium-235 nucleus and breaks it up into barium and krypton and three more neutrons. So whatever you started with, you take the mass of them, and whatever you ended up with, you take the mass of them. There will be a slight difference of mass. What has happened to this mass? This mass has been converted to energy. That is the nuclear energy that is generated in nuclear power stations, let us say, or, well, then you have this thing, nuclear weapons. So that is what it is. So energy and mass are now also unified through the speed of light within the same category. So you don't talk about energy being separately a conserved quantity or mass being separately a conserved quantity, but viewed together, taken together, they are conserved quantities. All of these things are happening. We don't experience them on our regular scale of nature that we experience through our senses, but on different scales of nature. So we are not designed to experience those scales. So from this, you can very well now have a little sense of the genius of Albert Einstein, that he was also a human being, just like all of us, and therefore he was not designed by nature to see these things, realize these things happen. Nevertheless, he did, right? So he transcended the boundaries set upon us through the evolutionary process, boundaries set upon our senses through the evolutionary process. So he was an extraordinary human being. You can very well sense that. Now we look at the second fundamental constant that I mentioned. So these are the four, let me see, before I go, these are the four implications of the speed of light in vacuum. C is a universally fixed quantity, universally fixed value of velocity through all frames of reference. Mass, length, and time are no longer very sacred mechanical dimensions. Because of the invariance of C, space and time are now unified into the same physical category, and because of the universality of the value of C, energy and mass are now equivalent of each other. Okay, now let's move on to Planck's constant. Planck's constant, it says that, I mean, in the last class we discussed that what is H? H is something, wherever you see H, just make sure of that one fact. Wherever you see H, be it understood by you immediately that things have been quantized, meaning that you are now talking about irreducible non-zero minimum quantities. Like when you say E is equal to H nu, meaning that that's the minimum quantum of energy. We talked about the Planck length and the Planck time. There's a slight error over here. It should be LPL and TPL, right? Planck length and Planck time. They quantize space and time, meaning that this length is probably the lowest possible least count of nature. The minimum, I mean, that's the least count of nature in space. And similarly, this TP, Planck time, is the least count of nature in time. Like whenever you have a least count or the minimum irreducible quantum, you give it a quantum name. What is the quantum name? Like the minimum irreducible electromagnetic quantum of energy is called photon. Light is an electromagnetic wave. So when you quantize that wave and make it particle-like, you give that quantum a name photon. Similarly, the minimum irreducible quantum of magnetism is the magneton. The minimum irreducible quantum of sound, sound as in phone, light as in photo, therefore photon, sound as in phone, or acoustic wave, that is, sound as that. So phone, from phone, you have got phonon. And so it is that some people have imaginatively given the name to the quantum of time, the word chronon. Chronon meaning, like, let's say, synchronous, happening at the same time. Or you say that in the chronological order, meaning in the order of time, or reverse, you say you are told, prepare your CV in the reverse chronological order, meaning the latest information comes to the top. So chronos, these things are related to time. So the minimum irreducible quantum of time, very probably given, probably, I wouldn't say very probably given by Planck time, is known as chronon, but it's just a name that's not in very regular circulation. So I have not written it, made it a part of the notes. So space and time are now quantized. Otherwise, we would have thought that can't we just go to, we talk about infinitesimals, right? Make it infinitesimal. Infinitesimal meaning that you can make as small as you can, but not exactly zero. That is the way we learn calculus. But nature can not exactly I mean, probably nature doesn't accommodate infinitesimals. Why can't nature accommodate infinitesimals? Because nature can't accommodate infinity either, 1/0 kind of a thing. The universe is finite. Therefore, everything within the universe has to be finite. And if everything within the universe has to be finite, then the reverse of finite ought not to happen either. I'm sorry, the reverse of infinity, uh, sorry, if everything about the universe is finite, the universe has a finite space, the universe has a finite lifetime, all these things, therefore the universe does not, physically speaking, the universe does not accommodate infinities. So if infinity is not accommodated, then the inverse of infinity, the reverse of infinity is zero. 1 upon infinity is zero. Then if the universe doesn't accommodate infinity, then the universe doesn't accommodate zero either. Zero is something that exists in the mathematician's mind, just as infinity is. So mathematics in that sense is actually a branch of philosophy, except that mathematicians also quantify their philosophical musings. But we are doing physics. We will use mathematics insofar as it is needed, but we will also see that there are things that really do not coincide with our mathematical understanding or the mathematical language with which we express the universe or articulate about the universe. Infinitesimal calculus is probably one such thing. Why I'm saying probably? Because nobody has still been able to design the experiment that will probe Planck length. It is 10 raised to minus 35 meter in the last class we discussed. Right. Okay. Now let us see something else. With h not equal to 0, wave-particle duality is established. We are now looking at the implications of Planck's constant. With h not equal to 0, the wave-particle duality is established. Now, what do you mean by wave-particle duality? Let us discuss this thing in some detail now. Just a minute, I'm sorry. Yeah, let us discuss this thing in some detail now, this whole wave-particle duality business. Wave-particle duality unifies, just see, I've written something, light is a wave, isn't so? You have studied this thing in the last semester. Barely 2 months ago, you studied electromagnetic, that light is an electromagnetic wave. And as a wave, it will go like this. And it's very much like water waves. You have a still water surface, you throw stone on that water surface, and it will create waves that will move forward. Right. So light is also something like that. It's a transverse electromagnetic wave. Instead of water, you need both the electric and the magnetic field. Instead of a stone that is disturbing the water surface, you need a charged particle to accelerate within the electromagnetic field, and the charged particle will radiate energy. And what will happen to the energy? The energy will start creating ripples in the electromagnetic field, just like a stone enters the water surface with some kinetic energy, and then it imparts a part of the kinetic energy to the water, and that kinetic energy is carried away as a disturbance, as a wave. The wave is the disturbance, right? So light is an electromagnetic wave. Very well, that is all very good. But then once again, thanks to Albert Einstein, light is shown to be a particle, a photon. So light can both be a wave and a particle. Now, okay, that's fine. But then we have also seen for ourselves just a while ago that light can never rest. So a photon is a very strange kind of a particle that never rests. Um, so it's like saying that this thing is a wave and a particle. The particle, I mean, the photon is a very strange thing. If you put all the ideas together, it's a very strange thing, this whole light business, because photon is a particle that is traveling at the speed of light. If it is traveling at the speed of light, then it will also see the universe to be contracted to a zero dimension, zero length dimension. That is, the length of the universe will be zero. So when you travel at the speed of light, what will be the universe? What will the universe look like? Incidentally, that's a famous question asked by Einstein himself. What would I see the world to be if I travel at the speed of light? So anyway, and the answer to that question gave a completely new direction to the course of human history. And he started it all. Anyway, photons have no rest. So photons have no rest. So we will also associate wave particle duality to particles that are moving, like let's say an electron or a tennis ball, or even you running on the ground, whatever. So you're looking at a moving material particle. A material particle point is very important because photons do not have rest mass. Photons have no rest. Very important point. Sorry, I should stress on this point. Photons have no rest. If photons have no rest, therefore, there is no frame of reference where you can measure, because the photons are always traveling at the speed of light. And the speed of light is an absolute value. Follow this point. It's a subtle point, but an extremely important point. Follow this point carefully with extreme attentiveness. If photons are always traveling at the speed of light, there is no frame of reference where you can make a photon go to rest. Therefore, a photon does not have any rest mass. There is no rest mass for a photon. M naught for a photon is zero. Okay. But material particles do have rest mass. I mean, you are at the moment are sitting at your home, and your parent or whoever is in the neighborhood will see you sitting. So you will have a rest mass. After a while ago, you may decide to take a jog outside in the garden or wherever. Your parents will see you running. So i- ideally, they should be seeing a different kind of a mass for you because you have a certain velocity now by Einstein's relativity. But that doesn't happen. No, I mean, it happens, but you wouldn't realize it. You wouldn't know. But we are using it using the way that analogy. So if light, now you follow Louis de Broglie's famous analogy. If light, which was a wave, becomes a particle that does not rest, then material particles, when they move, ought to show the reverse property. Light is a wave, an electromagnetic wave. Suddenly it has acquired particle-like attributes. It has become a photon. Objects that you see all around are material objects. They are made up of atoms and particles, molecules, all these things. Your paperweight, your mobile phone, your pen, your car outside, your piece of furniture, these are material particles, right? So when when you have a material particle that is moving, then they should also have a wave-like property going by the reverse way. What was a wave earlier, light that is, becomes a particle. What were particles earlier can therefore, by the reverse argument, become like waves. Okay. And so they can be, if they have a wave, if they are like waves, then they should have a wavelength, and this is the wavelength of material particles. The formula of that was provided by Louis de Broglie. Louis de Broglie wavelength of a material particle, lambda is equal to h by p, where p, small p, is the momentum, h divided by mv. Right. Now you follow this point extremely carefully. What is the role of h? As I said, it has probably set up a quantum of space and time. That was the first implication, number one. Number two, we are looking at it is connecting in nature, it is connecting wave-like behavior of material particles, material of matter with particle with their particle-like behavior. If you look at the right-hand side of this formula, lambda is equal to h by p. What is P? P is a momentum. P is momentum. A momentum is something that you attribute with material particles. I throw a cricket ball at you. If I throw it softly, you'd be able to catch it comfortably. If I throw the cricket ball at you very hard, you catch it, but you will not feel very comfortable catching a very fast moving cricket ball. Why not? Because it will impart a large amount of momentum to your hands when you catch it, right? So momentum is something that we associate with moving particles. A bullet is traveling, transferring a huge momentum. A tennis ball thrown softly still has a momentum, a soft, small momentum, whatever. Also, such sorts of things. So the right-hand side has got of this formula. It's a very simple formula, but the right-hand side, but it's a profound formula. Profound things of nature come in very simple packages, by the way. For instance, F is equal to ma, right? And so it is E is equal to mc squared. They're all very profound formulas. F is equal to ma took Isaac Newton to figure out. E is equal to mc squared took Albert Einstein to figure out. They come in very simple packages, but they carry a lot of punch, physics-wise. And so it is lambda is equal to h by p is also a very simple formula to work with, nothing very complicated. Uh, but look at this, the implication of this formula. The right-hand side gives you a particle-like attribute, and the left-hand side gives a wave-like attribute. And the bridge between the two is h. If h were to have a zero value, zero, then lambda and p would not have been connected to each other. But the fact is that I've written something over here. The non-zero value of h here connects the wave-like property through the wavelength on the left-hand side to the particle-like property through the momentum to the through the momentum p is equal to mv. Okay. Now you will very well say, so particles have wave-like behavior? Yes, indeed they do. And why don't you experience it? It's once again the same argument. Why don't you experience things that were just discussed a while ago? All these business of mass change, time dilation, length contraction. Why don't you experience those things? Because C is an enormously large number, right? And so it is that why don't you then experience wave like, are you a wave? Yes, indeed you are. But then why don't you experience that wave? The answer is that, like you don't experience Einstein's relativistic effect because C is a large number, so it is that you do not experience Louis de Broglie or Max Planck's wave-like effect, Louis de Broglie's wave-like effect of material particles, because h is actually a very small number. It is non-zero, but very small. Had it been larger, then it would have been easier for you to experience such things. Let us see how. This number is of the order of 10 raised to minus 34 joules second. That's a very small number on our scales. We see this number, joules second, these are units that we have defined in terms of the way we experience nature on our scales, right? Okay. And so since this thing is a very small number on the right-hand side, suppose you don't experience it readily because of the smallness. Let's see how. What is your mass? Your body mass is probably something around 70 kgs or so. If you're a young man, if you're a woman, probably 10 kgs less than that, something like that. That's a normal good weight. I mean, at this moment, you shouldn't be overweight. Maybe 20 or 30 years later, all of you will be having 10 or 20 kgs extra a weight, which is not very healthy, by the way. So right at the moment, your mass will be around 70 kgs, let's say. Okay, which is normal mass for young human beings. And you are, let's say, running at a jogging or walking, whatever, at velocities of the order of 1 or 2 meters per second. 10 meters per second is an extremely high velocity. It's a high speed. That's the speed of the fastest Olympic runners when they run for the 100-meter sprint event. So if you see that h divided by 70 into something like 1 or 2 meters per second. So 70, so something of the order of 70 or 100 SI unit in the denominator. So the wavelength will be 10 raised to minus 34 divided by something like 100. So 10 raised to minus 36 meter. That is the wavelength that you will have, your body will have. 10 raised to minus 36 meter. But 10 raised to minus 36 meter is hypothetically a very small number. It's even smaller than the Planck length scale. Planck length scale is something like 10 raised to minus 35 meter. So you will not appreciate your wave-like attribute because of the smallness of the value h. But then, are these wave-like attributes experienced anywhere in the universe? Yes, indeed. Anywhere in nature? Yes, indeed. When you have a particle whose mass is very small, such as the mass of an electron. Mass of an electron is of the order is 9 into 10 raised to minus 31 kg. This is 10 raised to minus 34 divided by the mass of an electron, 10 raised to minus 30. 9 into 10 raised to minus 31 is roughly 10 raised to minus 30. So immediately you will see an electron is traveling very slowly, right? Make it a small number. So immediately your wavelength will be of the order of something that you can measure. 10 raised to minus 4 meter or 10 raised to minus 4 meter is a fraction of a millimeter. 10 raised to minus 3 meter is a millimeter, right? A fraction of a millimeter. And that is the principle that you can use for slow moving electrons. Incidentally, I believe you would have read of the, or you are aware of the existence of a gadget known as an electron microscope. An electron microscope uses this thing, the wave-like behavior of electrons. Just to give you a simple example, so when objects become very small in mass, you experience nature on a scale of mass, which is let's go back to our table. The smallest scale of mass that you can experience is something like a milligram or fraction of a milligram. That's nothing. Uh, I mean, uh, that is small enough by your standards, but that smallness is nothing compared to the smallness of Planck's constant. So that is why, so I have written this statement. We do not experience this wave-particle duality through our senses, but the wave-particle duality becomes appreciable or something that you can experience when you have particles with small mass, such as an electron. Hence, wave-particle duality applies well to atomic and nuclear particles. In the atomic and nuclear domain, the wave-particle duality is very much an experienced reality. But nature has not designed you to look into an atom or a nucleus, right? Nature has designed you to look at nothing smaller than the size of, let's say, an ant or a very small insect, something of the scale of a fraction of a millimeter. You can't even see bacteria or virus. So, as you can see, I'm stressing this point again and again. Nature operates on vastly different, larger and smaller scales than what we may be able to appreciate through our senses. Now, let us look at one last point. I told you photons have no rest because photons are particles of light after all. And light will always travel at the speed of c, regardless of however fast you are traveling. And since they have no rest mass. Right. Nevertheless, by the wave-particle duality, an effective mass of photons can be found. What do you mean by that? What you're doing now is combining Einstein, Max Planck, and Louis de Broglie, all three of them together. Let's see how. E is equal to mc squared. Photons do not have any rest mass. So the idea of a rest mass or those things, M naught, those things don't apply. Nevertheless, photons have an energy. What is the energy of a photon? H nu. So if I divide h nu by c squared, I can manufacture a sort of an effective mass of photons. Manufacture an effective mass of photons. Effective mass of photons is E by c squared. This formula is Albert Einstein, E is equal to mc squared. And then what do you do about E? You write E is equal to h nu. That is Max Planck. Combine the two things together, or hc by lambda, whatever it is, E is equal to hc by lambda. And then you write h nu instead of E by c squared, and that is hc by lambda. Can you see something? Effective mass of a photon is inverse because h is a universal constant as much as c is. H and c don't change as you go from one frame of reference to another, as you go from one scale of universe to the other. These are fundamental constants. So these two things are constant. So the effective mass of a photon is inversely proportional to its wavelength. This requires some detailed discussion. Let us try to understand. I throw a stone at you, or not a stone, let's say a cricket ball at you, right? I throw a cricket ball, you're let's say, I mean, we used to play these games as children at school. It is a pretty dangerous game, throwing tennis balls or even cricket balls at one another. So if you are not able to catch it properly, it will hit you in the back or wherever, and you'll get hurt. If I throw the ball softly, you will not get hurt. But if I throw it very hard, you will get hurt. It's the same ball that is striking you. What is the difference between getting hurt and not getting hurt? It's the speed with which it has been thrown at you. So things that move fast and have some mass are likely to cause some injury. Okay. Let us now extend the idea to photons. Photons are particles. Follow this point carefully, extremely carefully. Photons are particles. All photons are particles of what? Particles of electromagnetic waves. Right. But the electromagnetic wave is not just light. It's a full spectrum, starting with radio waves, microwaves, infrared waves, the visible range optical spectrum, that is the sort of spectrum to which your eyes have been tuned by nature. Then beyond optical waves, optical range, you have the ultraviolet, then you have X-rays, then you have gamma rays, all sorts of things you have. So all of these things are electromagnetic waves. They all travel at the speed of light. So now you tell me, or you think of this question, that why is it that you're always able to converse on the phone, which is making use of radio waves probably, or you are cooking at home with the help of a microwave oven, which is again making use of electromagnetic waves. So these things are not supposed to cause you too much physical risk. But if you are exposed to gamma radiation continuously, that radiation will cause serious physical illnesses for you. Gamma rays travel at the speed of microwaves also. Both are electromagnetic waves. They travel with the speed of light. And if they both travel at the same speed, why is it advised that you don't allow yourself, incidentally, in medical technology, doctors use X-rays, right? But it is also advised that one must not have too much exposure to X-rays. One must not undergo too many X-ray tests because X-rays can cause physical harm. Gamma rays certainly do. But microwaves and radio waves don't do. Your telephones are using electromagnetic waves, radio waves probably, microwaves you use in the kitchen appliances. So why is it that both of them have gamma rays and microwaves have the same speed, and yet gamma ray exposure to gamma ray is is injurious to health, and not in the case of microwaves? I just gave you the discussion of throwing a cricket ball hard at you. If you get hit by the cricket ball, you'll be injured, but if the same cricket ball is thrown at you softly, you'll comfortably be able to catch it and feel nothing, really. The difference is that you get injured because in the case of the cricket ball is traveling faster. But here, microwave photons and gamma ray photons are traveling at the same speed. Then why is it that microwave photons are okay for your health and gamma ray photons can cause physical harm? Here is the answer in front of you. Effective mass of a photon is inversely proportional to its wavelength. Smaller the wavelength, greater will be the effective mass. Gamma rays have wavelengths that are extremely small. X-rays have wavelengths of the order of 1 angstrom, right? Light, the light photons that you see, your eyes are receiving. Incidentally, your eyes are continuously receiving photons, which are all traveling at the speed of light, and your eyes are feeling nothing because of that. Because light has got a very large wavelength compared to gamma rays. The wavelength of light is from 4,000 angstrom to 7,000 angstrom. Microwaves are of the order of 10 raised to minus 6 meter. So that's why they are called microwaves, right? So the effective mass of light, microwaves, they are far smaller because they have large wavelength. So they are, if the effective mass, now you follow this point carefully. Effective mass is small. These photons are soft photons. They are not like particles, they are more like waves. But gamma rays, by having X-rays have 1 angstrom. Gamma rays have a wavelength of 1,000 times less than that. Right, something like 10 raised to 1 angstrom is 10 raised to minus 10 meter. Yes, 1 angstrom is 10 raised to minus 10 meter. Whereas gamma rays have a wavelength of 10 raised to minus 2. Sorry, I'm sorry, I think I made a mistaken statement. X-rays have a wavelength of something of the order of 10 raised to minus 10 meter. Gamma rays have wavelengths of the order of 10 raised to minus 12 to 10 raised to minus 15 meters, right? Femtometers. So you can see X-rays about 1,000 to 1 lakh times longer in wavelength compared to gamma rays. So smaller, the gamma ray photons are extremely small. If they're extremely small, their effective mass becomes extremely large. And as such, they are like having larger effective mass. They are more particle-like, but not quite like particles. They are still waves. Wave particle reality will say that they are both, but they have larger effective mass and they are now like particles. So they are like, if you are continuously exposed to gamma rays, they'll be like bullets of photons tearing through you, and even as they are tearing through you, they are causing a lot of tissue damage. They are causing a lot of changes in the DNA structure, because the DNA is made up of ADCT molecules. If you have studied seriously your school biology, and as though these photon bullets are traveling through, they are knocking molecules, atoms here and there out, and drilling through your body like but they will not leave any visible entry wound or exit wound like real bullets that are fired from a gun, right? But nevertheless, by dint of having very large effective mass, they have become like very hard particles, like hard particles, but not particles as in the form of a cricket ball or a bullet. But they will cause. But microwaves and light or radio waves, they have small effective mass, so they are like soft massed photons or more wave-like. Gamma rays are more particle-like, microwaves are more wave-like, but both are, I mean, both gamma rays and microwaves are both like particles as well as waves. Anyway, so that is the answer. Okay, so we have looked at the physical implication of Planck's constant. Now let us look at Newton's gravitational constant, capital G. In order to do so, we shall look at something that you are familiar with, namely escape velocity. What is escape velocity? You throw a tennis ball towards the sky. You are not a superman or superhuman, so you will throw it with a certain high speed, whatever it is that human beings are capable of, something of that order. But it can't overcome Earth's gravity, so it will eventually fall down. What happens? You initially throw it with a high speed. Your initial the kinetic energy of the ball initially is quite high. Then it is going up and up, and even as it is going up, it has to work its way against the Earth's gravity, which is trying to pull it down. So there will come a stage when, and so basically when it is working its way against Earth's gravity, it is using up the reserve of kinetic energy that it has. So eventually there will come a stage when it will have run out of its full reserve of kinetic energy, and it will start falling back again. So it will momentarily stop when its kinetic energy will be zero. It would have used all of its kinetic energy to overcome Earth's gravity, and then beyond a point, it will no longer go higher and start falling back down again towards the Earth. Okay, but if you impart higher and greater velocities, it is a matter of your common experience that things will keep going higher and higher and higher. So eventually, it is possible that you'll impart a certain velocity beyond which, I mean, objects don't come back to Earth, right? So there will be a certain high enough velocity. If a particle attains that velocity, then it will not come back to Earth. So an object, such an velocity is known as the escape velocity. VESC, as in escape, is needed to escape gravity. So that object imparted that initial velocity will no longer come back to Earth. So let us see, how do we get this thing? Force is mass into acceleration, ddt of V, and we are now doing a little manipulation by calculus chain rule. We are writing m dv dt as m dv dr into dr dt. And what is dr dt? Dr dt is velocity. mv dv dr is equal to gravity, gravitational attraction, Newton's gravitational law, minus g capital M small m by r squared, where m is, let us say, capital M is the radius, the mass of the Earth, or whatever. And small m is the mass of the tennis ball or whatever you're throwing up. So these two masses, small m and small m, will cancel on both sides. And then you can put your calculus, integral calculus, as you can have on the left-hand side. Small m and small m have cancelled out from both sides, and you've got v dv, starting with the escape velocity. And here you have minus capital G capital M by r squared, starting from the radius of the Earth. R naught is the radius of the Earth. At the radius of the Earth, you have imparted an escape velocity. What is the escape velocity supposed to do? With that energy, the particle will completely go out of the Earth's gravity. But where does Earth's gravity finally go to zero? The Earth's gravity actually goes to zero at infinity, because it's minus gm by r squared. When r becomes infinity, this gravitational force will be zero. So you'll have to take the particle all the way to infinity, where its velocity will become zero. If you impart greater velocity, then it will be non-zero, whatever. But anyway, so where the particle, having completely escaped Earth's gravity, finally comes to rest. So V escape is the lower limit, zero is the upper limit for velocity, R naught is the lower limit for the radial coordinate, which is the Earth's radius, and infinity is the ultimate destination. Integration is not a challenge, I hope, for you. So the left-hand side is, as written over here, travel to infinity. The left-hand side will give you v squared by 2, lower limit is v escape, upper limit is 0. Right-hand side, now let us see, minus gm. Then when you take r raised to minus 2 and integrate it, it will be minus 1 divided by minus 1 into r raised to minus 1. Okay, r naught to infinity. This minus and this minus will cancel. Follow carefully. This minus and this minus will cancel. Upper limit for the velocity will be 0. Upper limit for gm by r with r equal to infinity will be 0. So the upper limits are cancelling. So the lower limit, when you put the lower limit, it will be minus v escape squared by 2. And on the right hand side, it will be minus gm by r naught. The two minuses will cancel again. And this is what you have. V escape squared is equal to 2gm by r naught. So square root of that will give you the escape velocity. Here, just a small diagram. Radius of a planet or star, whatever, it can be your R naught. Although I gave you the example of Earth as a matter of common experience. That's the only planet we all know. This principle can apply to any other spherical object, spherical planet. Now let us see what we can do. What is the fastest speed attainable in the universe? Just a while ago, we discussed that is the speed of light, right? So again, we fall back on our common experience. In the night, if the sky is clear, it's clear and dark, moonless night, you can go outside and shine a torchlight towards the heavens. You will see a sharp beam of light coming out of your torch and cutting through the sky and going out all the way to infinity. That does not come back. But if you throw a tennis ball upwards, it will come back and fall in your hands. So, light, of course, has got an enormously large velocity as compared to the required escape velocity. For planet Earth, the escape velocity that is required is 11 kilometers per second, 11.2 kilometers per second, which you have studied at school. It's a very simple matter of common experience, 11.2 kilometers per second. Light travels at 3 lakh kilometers per second. Light has no difficulty escaping the Earth's gravity. Okay, but let us look at this formula. I'm now increasing the required escape velocity by increasing the mass of a planet. See, the larger the mass, smaller the radius of a planet or a star, m is large, radius is small. Then this ratio will be large. If this ratio is large, then the corresponding escape velocity will be large. So you can keep balancing the two. This is an equation. The right-hand side increases. How can you increase the right-hand side? Make m large, r small, r naught small. And to balance the largeness, you'll have to also make v escape become large. But then v escape can only go up to a certain maximum value, which is the speed of light, maximum possible velocity. If that happens, then that is just the borderline case where even light cannot escape. If the right-hand side becomes so large that the left-hand side will require an escape velocity that is greater than the speed of light, then light cannot escape. So what have you got on your hands right now? I think you should know the answer. When light is unable to escape the strong gravity of an object, that object is known as a black hole. So what is the requirements of a black hole? Let's see now. So the specific requirement of a black hole is, you just put the value c squared on the left-hand side. Then you divide by 2g using this formula. C squared by 2g is equal to m divided by rs. Rs is equal to 2gm by c squared. What am I up to? This is the condition to trap light by gravity. This sort of a black hole, R naught, when it write it as capital R with a subscript S, is known as the Schwarzschild radius. Schwarzschild is Karl Schwarzschild, who gave the theory of this thing, the Schwarzschild radius of a spherical black hole. So the Schwarzschild radius of a spherical black hole, if you know the mass of an object, G is a universal gravitational constant. Newton's gravitational constant, capital G, is a universal gravitational constant. C, of course, thanks to Einstein, is also a universal constant. So mass is large. I'm sorry, if you know the mass, you'll immediately be able to know what is the Schwarzschild radius of that black hole. So what is the requirement to create a black hole? Massive mass, very large mass, as you have over here, and small radius. All a large amount of matter packed into a sphere of small radius, compact massive objects is gives you a black hole, possibly a black hole. For instance, here I've just done a little calculation for you. For the Earth, the mass is 6 into 10 raised to 24 kg, right? If you want to convert the Earth to a black hole, the Earth does not trap light, right? But if you want to make the Earth trap light, just give me a minute, I'll finish this discussion. If you want to make the Earth trap light, you'll have to squeeze all of the Earth's mass, all of 6 into 10 raised to 24 kg, all the world's oceans, mountains, continents, human beings, animals, all the things, pyramids, buildings, everything will have to be squeezed into a radius of 9 millimeter. You'll have to squeeze all of the Earth's mass into a radius of 9 millimeter. Now, 9 millimeter is less than 1 centimeter. A little gap between your thumb and your index finger. That's the size of a marble. If you collapse all of the Earth's mass into the size of a small marble of radius 9 millimeter, the Earth will be able to trap light. So just one last point that I shall mention over here. Just give me a minute, as I said. Massive, large mass, small radius, compactly packed in, gives you a spherical black hole. The radius of such a spherical black hole is known as a Schwarzschild radius, and it is also known as the radius of an event horizon. What is an event horizon? Just on this point, I'll end. A horizon is something beyond which you can't see, right? You look out of your window, you'll see the horizon, because the Earth is a curved surface. Beyond the horizon, you don't see whatever is happening on the other side of the horizon, beyond the horizon. So it is that, because why don't you see? Because light doesn't come from there to your eyes. And so it is in a black hole, whatever is happening can't be seen outside the black hole, because light is not coming out of the surface of a black hole. Therefore, whatever events are happening on the other side of the surface of a black hole, if at all they happen, it's like a horizon beyond which you can't see. So the surface is known as an event horizon. The surface of a spherical black hole is also known as an event horizon. Anyway, I shall stop over here. I've taken 2 minutes extra. I'll just briefly mention one point, non-technical point, non-academic point. On Monday, you have a lab again. I will send you the link to the lab on Monday morning itself. Unlike my usual practice of sending it a day before, because the lab starts pretty late in the day at 2 p.m. So I'll send you that thing. In the lab, we will take up I shall not give you any new assignment this week. We shall take up the old assignment and have some more discussion. Meanwhile, from your side, if you have any problems that you have encountered so far in the lab work that I expect to have started, you can take up those problems. So it will be more like a discussion session on whatever we have considered in the last class, and then we will see how things can be improved. You can bring your experience so far of lab work to the table, right? So that is what we shall have. I'll send you the link tomorrow. Your batch has not been finalized yet, not in eCampus. So that's why I haven't been able to prepare your batch list. So, but hopefully it should be done sometime by next week. Anyway, I will stop the sharing. If you have any questions, you can ask me the questions. Otherwise, I shall stop the recording. Anyway, stop the recording. You have any questions to ask? You can ask me now. Otherwise, we
Yeah,
can.
sure.
Yes, sir.
So,